Hello everyone, I am Mehmet Yuce. I'm from Electrical and Computer System Engineering, Monash University in Melbourne, Australia. I'll be giving this talk about cuffless continuous blood pressure monitoring using wearable body sensors. This is the outline of my talk. I'll start with introduction and then I'll talk about the cuffless blood pressure measurement concept, and then I'll talk about cuffless blood pressure sensor devices which are based on ECG, optical radar and bioimpedance sensors. Radar and bioimpedance sensors are particularly done in my group to measure blood pressure in a cuffless manner. And then I'll be talking about continuous wave radar that we use to detect pre-ejection period, which is something that can be used to make the blood pressure measurement more accurate. And then I'll talk about some real-time wearable sensor that we use to continuously measure BP, and then the clinical study of our work as well. So the blood pressure is known as the silent killer. It affects our cardiovascular system significantly. Some of the issues we know are heart attack, stroke, and heart failure. They are significant issues that should be addressed, and blood pressure is the technique that is used to see if we can detect these medical issues. Of course, there are other effects as well, like vision loss and kidney diseases and failure as well. So what is BP? There are three important parameters related to BP that are used in medical diagnosis. One is systolic pressure value, which is the pressure that when heart from left ventricle ejecting the oxygenated blood into the aorta and of course to every part of the body, and then later the pressure is released. We call that diastolic pressure, and then we have mean value of the pressure. These are three important parameters that we use in medicine for diagnosis of cardiovascular systems. So if we have a look at available BP monitoring devices, the first one, which is the gold standard, is arterial line device. That's a device we put into the vessel to measure blood pressure. It is quite accurate, but is invasive, and it causes a lot of issues to the patients when it is used. And another common way of measuring blood pressure is non-invasive way, which is using cuff. These are some of the examples. Either cuff is used around the finger or around the arm. Again, for continuous way of measuring BP using such devices is very uncomfortable and cumbersome and inconvenient that it causes to the patient. The cuffless way of measuring BP has been a very emerging research topic recently. The reason for that, it can be continuous, not like cuff. Cuff ones are not continuous, and it can be continuous, and it can be done without having any discomfort to the patients or to the people who are using such devices. If you have a look at the theory of blood pressure concept, we can start with the pulse wave velocity, which is a common equation is given by this. The pulse into our vessel can be expressed with this equation, and then the time delay is the time that the pulse going from one location to another location, assuming that has a length of L, can be given by by this equation. So which means, and the blood pressure pulse wave velocity actually is related to the blood pressure, and then time delay is related to the pulse wave velocity. So there are two concepts for pulse delay. One is called pulse arrival time. The other one is called pulse transition time, that researchers are focusing to use to measure or to estimate blood pressure from. So these are the two time delay parameters. So we need usually two sensors. In this diagram we have ECG, and then we have another sensor which could be detected from either optical or from another sensor. And then we're going to show in this talk that we use radar and bioimpedance to detect the second pulse. So the common way is using optical, which is PPG signal, and the time that defines that the blood is leaving the heart is R peak, and then reaching another location, which we will use another sensor, the red signal, to detect it, and there is a delay there which is called PAT. We can use several locations to detect PAT, whether it's minimum, maximum, or maximum slope. They all can be used to detect blood pressure. The PTT, this is something we're defining here, is different than PAT. In PAT we are using R peak of the ECG signal, but in case of PTT we don't use ECG, but we are using two pulse waves, which means we need to use two sensors on the body to detect two locations, and then we can have the time delay, which is again still linked to the pulse wave velocity. And then the difference between two, PAT includes PEP, so and then this is the relationship to define PEP here. And in terms of sensors, several sensors can be used to detect the pulse delay. If ECG is involved, ECG has to be on the location that you detect heart. It is chest, it could be anywhere. You can detect ECG even now around your wrist, and then you have other sensors detect the second signal, so to get PAT. So in our research, this is a diagram that we show. We use ECG on the chest and continuous wave radar targeting the aortic arc opening at the heart, and then bioimpedance at the chest to detect the pulse, and then we have PPG on the ear. So these are several body sensors that we used to analyze actually PAT. I'm going to explain some of these signals as I go through this talk. Of course, before you detect PAT or PTT, the signals on the body goes through some signal processing, and the signal processing blocks, whether they are filtering or using adaptive filtering or some other concepts to make the signals as clear as possible to detect the time delay. So in terms of PAT, it depends on where you get. We can call them PAT1, PAT2, but as I indicated, for radar, we are using radar for detecting PEP. So the difference between radar point, which is the green signal, and then bioimpedance signal, which was on the chest, is PTT, and then of course PAT is going to be from R peak to the point that you're using on the bioimpedance to detect PAT. So we take several locations of time delay, and then we try to map that into the blood pressure. If you have a look at only bioimpedance is ECG, so there's ECG. That's the time that blood is leaving the heart, going to the different locations. So in this case, this is the location on the chest close to the neck, there's going to be delay. As you can see, there's R, and then when we look at the peak of the waveform, there's a delay there. The way the bioimpedance works, and when the blood is coming between the sensors, we are using 2 electrodes for measuring bioimpedance, and then the impedance value is going to be in the minimum. So whereas this is the second case here, and when there's no blood yet, there's going to be the maximum point. In terms of the radar, the way radar works, you generate an RF signal, you transmit that into the body, and then it comes back, and you process that signal, and you detect the pulse at that point. We look at the radar signal together with ultrasound M-mode machine, just to make sure that the feature we are detecting on the radar is corresponding to the waveforms that is being used in actual medical environment. So in here, this is an ultrasound. M-mode is detecting from the heart. This IQ, actually we are using our own radar system. This is our device. As you can see, there's ECG, and then going into when the time that blood is leaving the heart, and then this is the waveform of the we have 2 IQ signal in radar, and there is a time delay between that. But there are more information radar actually is providing, which we are still working on to see what else we can detect from using radar when it's radar on the chest. This is just a video showing how we put the radars on the chest, and then we are using additional devices, which is the cuff devices, for reference. These are the signals, the screen that we detect the signals from radar sensor, and then we look at in different conditions, standing, sitting, blood pressure is going to vary. We just want to make sure that all those conditions, when blood pressure is changing, our signals are giving different time delay values as well. This is a signal, an example of a signal, ECG, and then it's continuous waveform. The foot of the signal between that and our peak actually is a PEP. We realized it's PEP value, and then we analyzed that for our blood pressure measurement. To detect that, there are ways of doing that. Say this is the continuous wave radar signal, second derivative, we find that point. For maximum transition, use the first derivative. In terms of the clinical trial, we conducted a clinical trial at Cabernet Hospital in Melbourne on around 41 patients, and the protocol we have are the stationed positions as well as when we exercise, and we also actually gave medication to reduce the blood pressure, so just to see we can follow the blood pressure when it is reduced. This is how we put into different time slots so that we can actually use the cuff device to measure, to get the reference. So we have a sitting for 3 minutes, another sitting for 3 minutes as an example, which means during the sitting we have 2 cuff values to make sure that we detect sufficient reference values for comparison, and then of course for developing the model as well. For exercise, there are several situations that we do when the subject did exercise, and right after that we measure it. Still the blood pressure is high, and then we measure using cuff as well. In terms of medication, which is GTN medication, we spray into the mouth, and the blood pressure is changing. In some cases is reducing quite significantly, and then we're measuring both the cuff value as well as using our time delay measurement techniques I provided information earlier. This is the blood pressure measurements together with PTT time delay in case of the still positions with sitting, standing, and then also in case of the exercise. As you can see, whenever blood pressure is going down, the PTT is going down, blood pressure is going up. So there is an inverse correlation. That's what we wanted to see so that we can develop the models. Similar here, you can see that whenever blood pressure going up and the time delay is going down, this is what we wanted to see to develop the model. This is for when we have the medication and spray the medication. Again, blood pressure is going down and then PTT going up. That's what we wanted. When we gave the medication, the blood pressure, we wanted to go down and to track it as well, not just always going up. In case of the exercise, we wanted to blood pressure value to go down so that we can measure it. In some scenarios, a subject body which actually resisting towards the spray, despite that is going down, it goes fast back to the normal. So different body had different reactions to the blood pressure, and it was interesting to see. We're going to look into this a little bit more in detail. In terms of blood pressure models, these are from literature actually. So there are, as I indicated, there is an inverse relationship between blood pressure and PTT time delay, but there are other models that we could look into. First of all, if you can get PEP, as in case of radar views, we could detect PEP. You can put that into the model as well, and then you can have several points, not just the landmarks. One landmark, you can have several landmarks to be involved as well to look at the model, and then we convey all of them. But the best model was this model, and including heart rate. As you can see, this is the percentage in terms of accuracy, which we define here to be less than 10 millimeter mercury, and it in some cases 90%, but most of the time it was more than 80% accuracy that we obtained using our own model. These are some graphical display of estimation as well as reference blood pressure, and as you can see, most of the values are within the 10 millimeter mercury, and we divide that into the posture and exercise. We just wanted to see how they are in terms of in different conditions, and overall the model was showing a good the accuracy correlation with the measured blood pressure. These are all the data we have, and use again posture and exercise and then medication, and you can see most of the data are within the -10 millimeter mercury region. So that was our first project that we conducted, and we also check other sensor locations. In this scenario, by impedance on the chest, staying on the chest, we assume that PPG, say you are wearing a watch, is on your arm, somewhere on your arm location. So that in that case, of course, it's going to be PTT. As you can see, we have two signals, by impedance as well as PPG. And in here we have two PPGs actually, so we can look at different locations, because it takes time from heart to go into the one PPG and then the other PPG. There's going to be time delay. We see that time delay in our waveforms, and then we use the PTT, and then the estimated blood pressure. This is the blood pressure value, and then as you can see, we increase and decrease blood pressure, and we observed that in our estimated blood pressure measurement. In another device is a chest space that we developed, and is an ECG as well as PPG signal, which is an optical signal. So that the time difference between R peak to PPG is going to be PAT in this case, because we are using ECG. Whenever you use ECG, is known as PAT. And of course, this is the detail of the model. We have the offline training, and then in case of real online validation, then we provide all the parameters into the model. This is just the setup that have our own measured the sensors, ECG, PPG, and the blood pressure, systolic, diastolic. This is the commercial device, which is FinaPress. It is a device that providing continuous blood pressure, so we wanted to compare both. This is FinaPress on the left arm, and the subject is exercising, and then this is our blood pressure. Now he's exercising, blood pressure is going up, and the same thing here with the commercial device is going up as well. So as you can see from the first screen, this is our own device, and estimated blood pressure. This is the one that from the commercial device. These are some data showing that the estimated blood pressure from our device is corresponding to the one that is actually obtained from the FinaPress, which is a commercial device. To show more in detail, we look at the error difference. It was around 5 millimeter mercury in case of online. This is a wearable device we developed for a bioimpedance. It's quite small. It can be placed on the chest. It's a bioimpedance sensor. As I said, you need the second pulse for measuring the delay if you're using ECG or you're using PPG. But this is the bioimpedance board that actually we developed in a circular manner. This is the detail of the hardware. And this is our radar device. We have radar developed in a continuous wave radar. It is integrated with the Bluetooth for wireless communication. These are the antenna that we used to send continuous wave and receive the continuous waveform. At the moment, we are collaborating with a company called Choicemat. They produce wristwatch, wristband devices. They measure SpO2 and other parameters, and now we are using ECG together with them and PPG in their device and to detect the blood pressure. This is somehow time delay, and that we detect from using their wearable wristband devices. And these are the references I have used in this talk. I'd like to acknowledge my students working on this topic and also my collaborators on this topic. And I'd like to thank all for listening to this talk, and have a good day.